So let's begin. Physical processes. So hopefully your teachers kind of talked about these at the beginning of the year, but there's two types of changes that we can observe in the chemical world. And they are definitely not like arbitrary. Like what I mean by that is it's not either this one or that one. But we're going to try to set up a set rule to kind of help us identify whether or not it's a physical process or a chemical process, a physical reaction or a chemical reaction, a physical change or a chemical change. So a physical process is going to be any time that matter undergoes a change, but the identity of that substance remains unchanged. The composition is like completely the same as it was when it went into the reaction. The best clue to this is identifying and looking at the chemical equation of the thing you're using, or the chemical formula of the thing you're using. Some of the biggest examples of physical processes are going to be phase changes or state changes. When you're melting, boiling, evaporating, condensing, going from the solid to liquid state, liquid to gas state, gas to solid state. The identity of the substance does not change, and therefore it is considered a physical process or a physical change. And another one that isn't as obvious is going to be the formation of a mixture. And the key words for that is going to be dissolving. When an ionic compound like salt dissolves into water, it's still salt and it's still water. They are just a mixture of salt and water. No chemical reaction happened. No chemical reaction occurred. So just kind of giving you a few examples of physical processes. We'll kind of go through the list here. Once again, sodium chloride NaCl in the solid phase, turning into NaCl in the aqueous phase. We'll be seeing these symbols a lot. Solid is represented by the S. AQ is referring to aqueous, which is essentially dissolved in water. Notice the prefix for aqueous is aqua, water. Water going from the gas phase to the liquid phase, this would be condensation. And one of my favorite demos is going to be sodium acetate coming undissolved from solution. So notice that in every single one of these situations, you have the chemical formula on the left side and the chemical formula on the right side. They are identical. It's NaCl, then NaCl, H2O, H2O, and of course NaC2H3O2 turning into NaC2H3O2. So as far as these go, these are going to be examples of physical changes. These are going to be examples of physical changes. And that's pretty much where we're ending with physical changes. For the rest of today, I'm really going to be focused on chemical reactions. And I might come back to physical changes a few times, but really we're looking at how atoms will break and form new bonds, which is going to be a chemical reaction. So what are chemical reactions? And hopefully if you can kind of make a connection to the physical process, which we just talked about, a chemical reaction is going to occur when the actual bonds or composition of the substance changes in a significant way. Like the atom A is bonded to atom B, atom A is now bonded to atom C. In a reaction, atoms will always break old bonds, rearrange themselves, and form new ones. That's always going to be the process of a chemical reaction. So some really awesome examples of chemical reactions, which we're going to talk about a lot today, but one of my favorites is igniting magnesium ribbon on fire. If you've ever seen this, I would or if you haven't seen this rather, I would highly recommend like looking this up on YouTube or something like that. But basically, if you ignite a piece of magnesium on fire, it releases an incredible amount of energy, and it's extremely bright. You almost can't even look directly at it. So that kind of gets us to the next point. Like when I'm observing processes occur or reactions occur, how do I know I'm actually looking at a chemical reaction versus just matter changing? And there are 4 pretty significant, obvious pieces of evidence for a reaction to occur. So the first one is going to be the production of energy. This almost always comes in the form of heat or light. And as we all know as chemists, heat and light is fire. So fire is an excellent evidence of a reaction, and a good word for us to know, and we'll talk a little bit about combustion reactions later, is combustion. Anytime something combusts, it is a chemical reaction, and oftentimes a product, if you will, of a combustion reaction is going to be fire. Another example of evidence of a reaction is going to be the formation of a gas. As far as gas formation goes, especially in solution, we oftentimes will see bubbles. If you mix A and B and you see the production of bubbles, it's probably going to be a chemical reaction. Third evidence of reaction is going to be precipitation. Precipitation is going to be the process of forming a solid when two solutions mix. Remember, oftentimes aqueous solutions are liquid, but solution doesn't always have to refer to something mixed in liquid. For precipitation reactions, it does. A precipitate is the solid that forms when two solutions mix. And once again, if you mix two things together and you see that precipitate, it's evidence that a reaction occurred. And last but not least, color change. One awesome example of things that change color are going to be indicators. These are going to be chemicals that change color based on the pH. Whenever an indicator changes from one color to another, it's going to be evidence of a chemical reaction. Now, I kind of want to take a pause here. When we're looking at the evidence of a reaction, I can think of examples for almost every single one of these that would necessarily be a chemical reaction. For example, if I heat up water, the water starts getting excited, it starts moving around, and what eventually happens is the water begins to bubble. And the reason it's doing that is because it's boiling. But if you remember from earlier, boiling is not a chemical reaction. So you kind of have to take these four pieces of evidence with a grain of salt. They are good pieces of evidence for reactions to occur, but I always like to kind of remind my students when I'm talking about these pieces of evidence that these color changes or formation of gas or precipitation are almost unexpected. And what I mean by this is this. If I were to take a blue liquid and a yellow liquid and mix it together, I'm going to get a green liquid. That is absolutely not a color change in terms of a chemical reaction. When I'm talking about evidence of a reaction, I'm usually referring to mixing a clear liquid with another clear liquid and getting blue or pink, something that you didn't quite expect, not as obvious as, our kindergarten mixing of colors. So keep that on the back of your mind when we work through these evidence of reactions. Okay, with those out of the way, we can get into something that is, in my opinion, quite exciting. We can go ahead and talk about balancing equations. Balancing equations is incredibly important. When we're balancing chemical reactions, we need to try and make sure that the number and type of elements on both the left and right-hand side are the same. We do this in order to support the law of conservation of mass. The law of conservation of mass basically says that matter cannot be created or destroyed. The amount of stuff that goes into a reaction has to equal the amount of stuff that comes out of the reaction. It just doesn't go poof. It doesn't go into nothing. And atoms don't come from nowhere either. Once again, the process of balancing is such that you want to have the same number and type of elements on both the left and right-hand side of an equation. This has to happen in order for us to do things later on down the road like stoichiometry. Coefficients in representing chemical reactions is incredibly important as long as you are comfortable with this process. Last but not least, the way we balance chemical reactions is by adding coefficients. So what I'm going to do is this. Everyone's kind of at different abilities in terms of their skill level, especially when it comes to balancing. So I'm going to put up this unbalanced chemical reaction, and I want you to try it out. I want you to look at this process and see if you could figure out how to make the number of carbons, hydrogens, and oxygens equal the number of carbons, hydrogens, and oxygens on the right side. So you kind of have to work your way through this. I'll give you a few seconds to kind of consider this. And the way I approached this problem is first by adding a 2 in front of the water. By adding the 2 in front of the water, this allows for the number of hydrogens to equal the number of hydrogens on the left side. Now, if you're kind of looking at this, you have 1 carbon on the left, 1 carbon on the right, 4 hydrogens on the left, 4 on the right. And I'm kind of looking at this going, okay, cool. The last thing I need to balance is the oxygens. And great, that's really it. All I have to go ahead and do is add a 2 in front of the O2 to get the correct number of oxygens on both the left and right-hand side. So this would be an example of a balanced chemical equation. The number of carbons is equal on both the left and right-hand side. The number of hydrogens is equal, and the number of oxygens. So what I'm going to do is just kind of give you a handful of tricks for balancing. Now, these are not the end-all rules. Some balancing, I usually just tell my students, just go for it, and usually you'll figure it out. But with that being said, there are some really tricky and challenging balancing problems, so just kind of keep that in the back of your mind. So trick number one. Trick number one is to balance the element that appears the most in the equation last. So if we kind of go back to the example I was looking at here, notice that carbon appears once on the left side and once on the right side. Notice that hydrogen appears once on the left side and once on the right side. But oxygen appears in the oxygen molecule on the left, the carbon dioxide molecule on the right, and the water molecule on the right. So what I did intentionally was actually balance the oxygen molecule last. Balance the element that appears the most in the equation last. Trick number two. This one only works if polyatomic ions appear the same on both the left and right-hand side. However, if that's true, balance polyatomic ions as if they are their own element or particle. If you kind of break down the number of elements that are in the polyatomic ion, like sulfate or carbonate, it gets significantly more tricky, and I would not recommend it. I would kind of keep the sulfates and carbonates together rather than break them apart in terms of counting. And last but not least, when I balance these, I sometimes just keep track of my elements below the arrow, and I'll show you what I mean by this in the examples to come up. So what I want for you to do, I'm going to go ahead and give you all 3 unbalanced reactions. I want you to try to balance these unbalanced reactions using the tricks that I established up above. Not every single one will require one of the tricks, but it might be helpful for you to check those out. And what I'm going to do is I'm actually going to switch over to my whiteboard app and kind of show you how I would approach these unbalanced reactions. So there we go. Cool. So the first reaction I have is actually an awesome reaction. This reaction appears in rocket fuel. And it's nice because it produces nitrogen gas and water. So it's N2H4, so dinitrogen tetrahydride, reacting with dinitrogen tetroxide, so N2O4, to produce nitrogen gas, N2. Notice how I'm leaving myself a little bit of room in front of each of these compounds or elements, and water. Now I want to leave myself a little bit of room in front of each one of these here so I can place a coefficient if necessary. All right, so the first trick I gave you was to balance the element that appears the most last. There are 3 elements in this unbalanced equation. I have nitrogen, I have hydrogen, and I have oxygen. And it looks to me that hydrogen and oxygen both appear twice, once on the left and once on the right. And then nitrogen appears 3 times. It actually appears twice on the left and once on the right. So I'm actually going to balance nitrogen last. So let's kind of go through this. If you look on the left side, N2H4 has 4 hydrogens. And on the right-hand side, there's 2 hydrogens in water. I have 4 oxygens on the left and 1 oxygen in water. And then I have 4 nitrogens on the left and 2 nitrogens on the right. So it seems to me that this is not balanced because I don't have the same number or type of element on both the left and right-hand side. So let's get started with this. it seems to me that the most logical jump would be to add a 4 in front of water. By adding a 4 in front of water, this changes the number of hydrogens on the right-hand side to 8. But it does change the number of oxygens on the right-hand side to 4, equaling it out. So we're kind of getting there. Because I changed the number of hydrogens on the right-hand side to a number that's greater on the left-hand side, what I'm going to do is now add a coefficient of 2 in front of the N2H4 over on the left. By doing this, it changes the total number of nitrogens to 6 and the total number of hydrogens to 8. So it seems to me I balanced hydrogen and oxygen first because they appeared the least, and the last thing I have to balance is the nitrogen. In order to balance the nitrogen, all I need to do is add a 3 in front of the nitrogen molecule. At this point, I, of course, want to make sure if anyone ever has any questions, please feel free to ask, and I'd be more than happy to answer. It seems that there's a small viewing party right now, so we can definitely answer those questions whenever. But until then, I'm actually going to move on to the next unbalanced equation that I have. We're just going to go ahead and slide this down here. And the next unbalanced equation I have is as follows. It's aluminum sulfate, so Al2SO43 will react with lithium hydroxide, LiOH, to make, oh, one sec, I'm at school, so, to make AlOH3 and Li2SO4. All right, wonderful. All right, so as far as this one goes, the trick that we're going to be following is to balance the polyatomic ions. We're going to balance the polyatomic ions. It seems to me that all the elements appear pretty much the same on both the left and right-hand side. I have aluminum, sulfate, SO4, lithium, and then hydroxide. The first one has 2 aluminums on the left and 1 aluminum on the right. First one has 3 sulfates on the left and 1 sulfate on the right. I have 1 lithium on the left, 2 lithiums on the right, and 1 hydroxide on the left, 3 hydroxides on the right. So there's so many different things that I can kind of do, but why don't we just kind of work our way down the list? It seems to me that the aluminums are not balanced. So what I'm going to do is add a 2 in front of the aluminum hydroxide. By doing this, it changes the amount of aluminums to 2, but it also changes the amount of hydroxides to 6. Cool. The next one seems to be to balance the sulfates. In order to balance the sulfates, I need to add a 3 in front of lithium sulfate. This changes the amount of lithiums on the right-hand side to 3, equaling that out, and giving me a 6 on the right side. And if you're kind of paying attention here, you see that I have 6 lithiums and 6 hydroxides on the right-hand side, and only 1 of each. So all I have to do to balance this chemical reaction is put a 6 in front of this to even out the unbalanced elements on the right-hand side. And this would be our balanced reaction. We're going to go ahead and balance one last reaction, and then we're going to move on to looking at specific types of chemical reactions. The last reaction we're going to look at is going to be Fe3O4 and aluminum, making Fe and aluminum oxide, Al2O3. So let's go ahead and check this one out here. I like this particular problem mostly because this problem has the numbers of oxygens in wonky places. So I'm actually going to balance the oxygen first, even though oxygen, aluminum, and iron all appear the same amounts on both the left and right-hand side. The way I'm going to balance this is by using the subscript from the other elements. So if I look at oxygen's subscript right now, it's 4 on the left side, but 3 on the right side. So once again, I have 4 oxygens on the left, 3 oxygens on the right. I have 1 aluminum, 3 irons, and 1 iron. Oops, sorry, I have 2 aluminums on the right side here. 2, 3, and 1. So once again, if we look at the subscripts of oxygen, there's not really one coefficient that I can use to balance this. So what I'm going to actually do is use the 3 from the other side to balance the iron oxide on the front, and then the 4 from the other to balance the aluminum oxide. This gets me a total of 12 oxygens and 12 oxygens. That actually balanced the oxygen by using the subscript from the other one. This totally makes the iron and aluminum out of whack though. So aluminum becomes 8 and iron becomes 9. But what's so awesome about this is because we have individual elements or, elemental aluminum and iron, all I have to do is add the coefficient 8 and 9 to make this balance. And there we go. We have the correct number of iron and aluminum and oxygen, making this a balanced reaction. So once again, balancing can be super tricky. I've seen questions that have like ridiculous unbalanced equations that take forever, it seems like. The last trick I want to give you is this. If you ever find yourself going in a loop where you're like adding 2 in front of something, then a 3 in front of something, and then a 4, 5, 6, like it just kind of keeps going. In my opinion, the best thing to do is just erase your coefficients and start again. Sometimes that's the best thing you can do. So those are the unbalanced equations, or excuse me, the balanced equations. And if you need any help with those, please feel free to ask in the question bar over on the right-hand side. So until then, what we're going to actually do is we're going to continue on with our different types of chemical reactions now. Our reactions are once again going to be gone over in great detail this week. So really, I'm just going to give you what they are so you can keep an eye out for them when you do them in your class. So reaction type number 1. Precipitation reactions are awesome. You basically have this one solution and another solution, something dissolved into something dissolved, and you pour them together. A precipitation reaction is a reaction that produces a solid when 2 solutions or mixtures mix. Specifically, the language you want to look for is precipitate. A precipitate is the solid that is produced when those solutions are mixed. The way these balanced chemical reactions look have aqueous reactants. Remember, you're taking a solution and another solution, mixing them together to produce the precipitate. In this balanced chemical reaction, PbI2 would be the solid produced when 2 solutions mix, and therefore it would be your precipitate. And the precipitate is this awesome yellow mixture. That yellow cloud of stuff in there is solid, and if you were to let that just settle, it would quite literally fall to the bottom. And you could do stuff like filter out the precipitate to find out how much you actually collected in the chemical reaction. The next type of reaction that we're going to be looking at are acid-base reactions. Acid-base reactions require an acid and base. So what I thought I would discuss with you first is what are acids and bases. Now, this is an entire unit in the world of AP chemistry. So what I really want to do first is just kind of give you a broad definition of what they are. Acids are substances that donate protons, and a proton is going to be also considered the hydrogen ion. Many acids are written with the hydrogen in front. That hydrogen in front indicates a hydrogen that we can donate or get rid of. So that hydrogen in front is usually the acidic hydrogen. Bases, on the other hand, accept protons from acid. So for every acid in an acid-base reaction, you have to have a base where the hydrogen moves from the acid to the base. 2 very common examples of bases are going to be metal hydroxides. Remember, hydroxide is the polyatomic ion OH, and the metal is going to be anything else on the periodic table that's a metal. So for example, sodium hydroxide, potassium hydroxide, calcium hydroxides are all examples of bases. The other ones that are less common but good to know as a AP chemist are covalent molecules with nitrogen. Nitrogen can accept hydrogens because of its lone pair. So keep an eye out for nitrogens because they accept protons, they don't get rid of them. So let's go ahead and remind ourselves a couple examples. We have anything with a hydrogen written in front. So this HX, X is not an element, obviously, it's representing something else. So it could be like hydrochloric acid, which is HCl, sulfuric acid, which is H2SO4, et cetera, et cetera, et cetera. We can also have the metal hydroxides. Once again, that's represented with MOH. There is no element named M, so we can replace any other element, metal that's there. So lithium hydroxide, calcium hydroxide, et cetera, et cetera, et cetera. And then last but not least, covalent or molecular nitrogen. Ammonia, NH3, is an excellent example of a base. When it gets placed into water, it will actually take a hydrogen ion from the water, turning it into ammonium, which is NH4. We also have, it looks like dimethylamine, which is CH3, NHCH3. As far as this goes, the nitrogen in the middle still has a lone pair of electrons, which is willing to accept a hydrogen from something else. So keep an eye out for these things. All of these are examples, very common examples of acids and bases. So what is an acid-base reaction? Oftentimes we call acid-base reactions neutralizations. I've also heard them called titrations, but not all titrations are done with acids and bases, so just keep an eye out for that. Neutralization is a pretty good other word for an acid-base reaction. And essentially, what's going to happen is in an acid-base reaction, protons are always moved from the acid to the base. For a very generic type of acid-base reaction, we have acids reacting with metal hydroxides, which will almost always form, that should say water and salt. That should say water and salt. So I'm going to go ahead and quickly change that. I'll change it later. It should say water and salt, not an acid and salt. There we go. So for example, we could take sodium hydroxide, which is that metal hydroxide, react it with hydrochloric acid, and this will make NaCl, which is table salt, and water. We can also take calcium hydroxide, CaOH2, react it with hydrobromic acid to make, yes, this, water and calcium bromide. Now, I do want to remind everyone that the word salt in chemistry does not refer to table salt, which is sodium chloride. So this particular example, we have calcium bromide, which is an ionic compound. An acid-base reaction is any reaction where protons are moved between the acid and base. I'm saying it again because I need to make sure you understand that protons moving between reactants indicates an acid-base reaction. So notice that in this particular example, I have sodium bicarbonate reacting with acetic acid. Guess what? This is baking soda and vinegar. If I take baking soda, it will go ahead and donate the proton that it is in the bicarbonate and will, if I take vinegar, it will take the hydrogen ion that is in acetic acid and give it to the bicarbonate anion. What this does is it turns it into water and carbon dioxide. Carbonic acid spontaneously decomposes into water and carbon dioxide when in water. And that carbon dioxide that we see is the bubbles that are produced in that specific acid-base reaction. So I do want to point out that not all acid-base reactions produce bubbles, but when they produce carbonic acid, that's absolutely the case because carbonic acid will just spontaneously decompose into H2O and CO2. The last type of chemical reaction that we're going to look at, and I do want to point out that these are not like extremely specific reactions, but when they do these things like produce a solid or transfer protons, they are absolutely this generic class of precipitation or acid-base reaction respectively. Oxidation reactions are the last one. Oxidation and reduction are also called redox reactions. A redox reaction is going to be any reaction that transfers electrons between the reactants. One of the most common examples of a redox reaction is the combustion reaction. And hopefully at this point you've gone over combustion reactions with your teachers, but on the off chance that you have not, a combustion reaction is going to be when a hydrocarbon, something with carbons and hydrogens, reacts with oxygen gas, O2, to produce carbon dioxide and water, CO2 and H2O. So here is an example, of one of my favorite combustion reactions. This is propane, which is what fuels our barbecues, and I love a good barbecue. So C3H8, which is a hydrocarbon, it contains carbons and hydrogens, reacts with oxygen gas to produce water, H2O, and CO2. Now, I do want to remind everyone that combustion reactions also produce a ton of heat in the form of light and flames. Excuse me. Now, a cool little thing that I want you to think about: when things form bonds with oxygen, they actually become oxidized. So that's where that word comes from. Oxidization is when things form bonds with oxygen. So keep that on the back of your mind. It's not always true, but like 95% of the time when something forms a bond with oxygen, it itself is being oxidized. So for example, if I have copper oxide reacting with sodium, sodium will actually become oxidized when it forms a bond with oxygen. And interestingly enough, because copper lost the bond with oxygen, it became reduced. This is a super big generalization, but it's a good one for when you're practicing more specific and more heavy-duty oxidation reduction equations down the road. So keep that on the back of your mind. The last thing I want to talk about is that any type of synthesis or decomposition reaction are usually redox reactions. You're transferring electrons between the reactants to produce a new product. So for example, if I take iron and chlorine, I can go ahead and combine them to make iron 2 chloride. This is absolutely an example of a redox reaction. Electrons transferred from the solid iron to the chlorine, making iron positively charged and chlorine negatively charged. Also, when ammonia, NH3, decomposes into nitrogen gas and hydrogen gas respectively, electrons are transferred then too, and therefore this is absolutely considered a redox or oxidation reduction reaction. Notice that both of these reactions did not include oxygen. So the last thing that I want to go back to with that generalization I gave you is that just because a redox reaction occurs doesn't mean there has to be oxygen. Oxygen does not have to be in there for an oxidation reduction reaction to occur. And that's it. That's our general intro to chemical reactions. As with everything in the world of chemistry, we're going to get into a lot of these things in a lot of detail. So I want you to kind of get ready, get pumped. Hopefully, if you have any questions, I can take them now. It looks like we have a few people watching. And if you have any questions, I'll stay for a good 60 seconds waiting for questions to answer them. Otherwise, if you feel good, that's it for today. All right, awesome. Looks like we got a question from Matthew. What are the general rules for double displacement with oxygen? Do you mean like how do I identify what precipitates out? Double displacement, there's a couple of examples of them. But can you give me a little bit more specifics on what do you mean by the general rules? Otherwise, I could also go over to the whiteboard and look at some of those. Okay, I see what you're saying. So CaO and H2O make calcium hydroxide and hydrogen gas, probably. Yeah, let's check that out. So CaO and H2O. All right, so I'm gonna just switch over to my whiteboard app so we can see what's going on here. So I think with any double displacement reaction, you really want to identify what the ions you're looking at. So we have CaO and H2O. Whenever I'm trying to predict the products of any chemical reaction, I try to identify what the specific charged particles or substances are within them. Now, it's kind of weird because water is a molecule, so there aren't technically charged species within them. But there is a good rule for water. When you're trying to determine the products of a chemical reaction with water, it usually can be separated into hydrogen gas and hydroxide. So H plus and OH minus. Yeah. I totally know what this one is. Okay. Okay, so this is actually a special reaction. This is not actually a predict via the ions. This is the reverse of the decomposition of a metal hydroxide. So let me kind of show you what I mean by that. Sorry about that, Matthew. I just needed to kind of compose myself there. So the product of this is going to be calcium hydroxide, which is CaOH2, which is absolutely not dictated by the charges at all. There's a handful, and some chem teachers make you memorize a handful of these, and some don't. So I'll go over the ones you should kind of pay attention to first. So there are three. It's calcium hydroxide, or any metal hydroxide. And when metal hydroxides, MOH, decompose, they produce the metal oxide and water. Now, if you see, that's actually the reverse of what I've written. And the only reason that I could kind of pick up on the fact that calcium oxide and water would produce calcium hydroxide is because I had the other one memorized. And that's why it took me a second to kind of realize what was happening. So for example, if I had NaOH, this will decompose into the metal oxide. The metal oxide would be sodium and oxygen, and because sodium has a +1 charge and oxygen has a -2 charge, this would be Na2O and water, H2O. In order to balance this, you just put a 2 coefficient in the front there. So that's the first one. That's number 1. I'll put a 1 next to that so we can kind of keep an eye on that 1. The second one is going to be metal chlorates, metal chlorates, and remember chlorate is ClO3. These will always decompose into the metal chloride and oxygen gas. Those two, oxygen gas. So for example, with this one, if we go ahead and take potassium chlorate, KClO3, and heat it, we can actually decompose it into potassium chloride. So potassium chloride is going to have a +1 charge on the potassium, -1 charge on chlorine, so KCl, and then the oxygen gas is going to be O2. In order to balance this, we need to place a 2 in front of the KClO3 and a 3 in front of the O2 in order to get the correct number of oxygens, and then a 2 in front of the KCl. The last type of oxide decomposition that you should kind of pay attention to is the metal carbonate. So that's going to be metal bonded with, a metal bonded with the carbonate polyatomic ion, so CO3. And that's always going to produce the metal oxide and carbon dioxide, CO2. So a really cool example of this one is going to be calcium carbonate. If you heat this up, you'll actually produce calcium oxide. So calcium has a charge of +2, oxygen has a -2 charge, so it's just CaO, excuse me, and then carbon dioxide. So hopefully that helps answer your question, Matthew. I know it's kind of sucks to memorize things, but those are 3 really good examples of decomposition reactions. And when you brought up calcium oxide and water, I was able to identify, hey, water is the product of this special chemical reaction that produces a metal oxide and water, and we can just flip that around to figure out what the product of that reaction is. Awesome. Awesome, awesome, awesome. Yeah, predicting products can be kind of a pain, but really at the end of the day, Your best bet is going to be identifying the charges of each individual ion and then repairing them up down the road. We'll look at some specific examples when we do precipitation reactions and acid-base reactions. So hopefully that'll help more there. I'll wait another 30 seconds to see if there's any questions. With that being said, if that's it, I hope you guys have an awesome day. Should we know decomp of metal carbonates and water, though? That's kind of a weird question. And the reason I say that is because in the College Board world of decomposition reactions, they don't want you to memorize a huge amount of things. For example, in this unit, the big things that you're going to have to memorize are the solubility rules. But you only have to know the solubility rules for group 1 metals. So that's going to be the alkali metals. They are always soluble when they're bonded to something. Ammonium, which is NH4+, and nitrates, NO3-1, will always be soluble. Now, as far as you, Matthew, when you're looking at these carbonates and special decomposition reactions, this might be your teacher-specific thing, which is totally fine. I think understanding the decomposition reactions are necessary for chemistry, but maybe not necessary for the AP chemistry curriculum. Awesome. Cool. Great, y'all.